Hello, I'm Dr. Albert and thank you for joining me. Today we're going to solve this problem where we're going to find the area bounded by the functions f of x is 8x, g of x is 8 over x, and h of x is x squared. So in order to solve this, the first thing we should do is graph the three functions and determine what region we're talking about. Alright, now that we've graphed those three functions, we'll notice we have 8x here, 8 over x here, and x squared here. I'm trying to keep them coordinated so we can tell which one's which. But if we look for the area bounded by those three functions, you'll notice that the only area bounded by those is this area right here. And so what we're trying to do is we're trying to find the total area of that section right there. Now, in order to find the total area, what we're going to do is we're going to cut out cross sections, find the area of the cross sections, and then we're going to add up the area of all the cross sections in order to get the total area. Now, if we look at this, what we're going to get is I can draw in cross sections here, and they're going to look something like this over here. And we notice that we get a piece like that. And we can move these to the left and to the right, and that'll cover up most of the area. However, here we have that the upper bound on the cross section is the pink function, and over here it's the green function. So we'll have this is our upper and this is our lower function. Now over here though, that changes. It's no longer the 8x on top and the x squared on bottom, but rather it's the blue one on top and the x squared on bottom. So what we're going to get is we're going to get two different sections with two different cross sections. So I'm going to draw those in here. Now where those are going to split up is right here at this point, where I stop taking the red function as my upper function, I start taking the blue function as my upper function. In order to find the total area, I'm going to find the area of this piece, and then I'm going to find the area of this piece, and then I'm going to add them together. So I'm going to focus on the area of this piece for now. And as I do that, I'm going to find that the area of these cross sections, I'm going to call the area of the first cross sections is going to be the height of this rectangle times the width of this rectangle. So it's going to be height times width. Now the width of the rectangle, notice, is this distance right here. So what we're going to end up doing is, because we want to be able to make this a more accurate approximation, we're going to keep letting this distance get smaller so that we can get thinner rectangles as we go and we add them up. So this is actually going to be our changing in the x direction as far as how thick we want to make that. So what we get here is in the fact that delta x is equal to w. That is, the width of those rectangles is just the change in x. For the height of the rectangles, what we're going to get is, well, the height is going to be this value minus this value. Now these are each y values, so I'm going to call this the bigger y, and I'm going to call this the smaller y. So what we end up with is that the height of the rectangle is the bigger y minus the smaller y. Now the bigger y is the y value that corresponds to this function, and since that's our red function, that means that it is 8x. So here we get the bigger y is equal to 8x. And now the smaller y corresponds to the function, the green function, or that is the x squared. So we get our smaller y is x squared. So now combining that together, what we get is that the area of the cross sections for the first piece are really just going to be 8x minus x squared is the height times the delta x is the width. Now that we have the area of each cross section, we can find the total area by adding up all of them. And the way we add up all of them as we let the delta x go to 0 is we say that we take the integral on the interval that I'm interested in of the area of each of the cross sections. And so what I get is the integral from a to b of 8x minus x squared dx now, because we're letting delta x get infinitesimally small. So then I need to calculate the integral from a to b of 8x minus x squared dx. Before I do that though, I do need to find my limits of integration, so I need to find a and I need to find b. Now a is going to be the smallest x value I'm interested in, B is going to be the largest x value I'm interested in for this interval. So if I look at this interval, remember that's this region here, the smallest x value I'm interested in is this point right here. What's interesting about that point is that it's the intersection of the red function and the green function. So to find that point, which we're calling A, what we have to do is we have to let 8x be equal to x squared. So now if we want to solve 8x is equal to x squared, we can subtract 8x and we get 8x squared minus 8x. So 0 is x times x minus 8. So x is either 0 or 8. Now since we have two solutions, we have to determine which of the solutions is the correct one to use in this situation. And the way we do that is we look at the graph and we say, well, what makes sense here? Well, if I'm looking at the graph, this looks a lot more like 0 than 8, because 8 is way over here. So what I'm going to do is I'm going to say, okay, well then A is in fact going to be 0. So we'll say A is 0. Now, in order to find our B, or the ending of this interval, what I have to do is I have to find another intersection point. This intersection is going to be between the red and the blue function. So what we're going to do now is, well, instead of letting 8x be x squared, we're going to let 8x be equal to 8 over x. So to find B, we let 8x equal 8 over x, and we solve for x. In order to do that, I'm going to multiply by x, and I'll get 8x squared is 8. If I divide by 8, I get x squared is 1. Therefore, x is either the positive or negative 1. Now, in this situation, again, we're going to use our graph, which is why it was very helpful to draw it in the beginning, in order to see that, okay, well, here it is a positive value, so therefore I should take the x equals 1 as opposed to the x equals negative 1. And so we get that our upper limit for this interval is going to be 1. Hence, our total area is going to be the integral from 0 to 1 of 8x minus x squared dx. Now I'm going to leave that for a little bit, and I'll come back at the end and do that when I'm finding my total area. But at least we know this total area here is in fact going to be the integral from 0 to 1 of 8x minus x squared dx. Now that we've finished the first area, I'm going to move on to the second area. I noticed that I've erased things so that we have a little bit more room and we're a little less cluttered. And so now if I look at the second area, what we're going to have is we're going to again find the area of these cross sections. So the area of the second cross sections is going to be the height times the width. Now if we look at the width again, notice that we're going to want that to get smaller so that we can get a more accurate approximation until it becomes infinitesimally small. So we're going to let the width be our change in x, or our delta x. Now if we look at the height again, we're going to find that that's this distance here. So what I end up with is this y value minus this y value. So I'm going to call this my bigger y value, and this my smaller y value. So the height of the cross section is going to be the bigger y minus the smaller y. Now in order to actually find this, I have to figure out what those y's are in terms of x, just like I did last time. So I'll notice that the bigger y corresponds to the blue function, so the bigger y is in fact going to be 8 over x. So we're going to get 8 over x minus the smaller y is the y value that corresponds to the green function, or the x squared. And so what we get is s is x squared, and then the width is still delta x. So the area of these cross sections are going to be 8 over x minus x squared times delta x. Now again, if we want to find the total area, we're going to add up all of these cross sections as they become infinitesimally thin. So in order to do that, I'm going to say that my total area is going to be the integral from a to b of 8 over x minus x squared dx. Now again, I need to find my a and my b. So in this case, my a is my starting point, is right here. My b is my ending point, which is right here. And so we have to determine what makes those special. Well, the a is special because it's the intersection of the red and the blue function, or 8x is equal to 8 over x. Notice that we actually just found what that intersection was going to be. We determined that was x equals 1. So in this case, we're going to have a is equal to 1. Now we will have to find the b, and the b is going to be the intersection of the blue and the green line. So what we're going to have is, for finding b, we let 8 over x be equal to x squared. Now to solve this, I'm going to multiply by x and get 8 as x cubed. Therefore, x is the cube root of 8, or x is 2. So what that tells us is that b is in fact 2. So if I'm going to find this area, it's going to be the integral from 1 to 2 of 8 over x minus x squared dx. So the second portion is going to be the integral from 1 to 2 of 8 over x minus x squared. And so now what we have to do is we have to find that along with the first area, add them together in order to get the total area of both together. Alright, so we've erased the drawing so that we have more room on the chalkboard, and we've recalled the things that we had from earlier. That is, the first section was the integral from 0 to 1 of 8x minus x squared dx. The second area was the integral from 1 to 2 of 8 over x minus x squared dx. So my total area bounded by the curves is going to be this integral plus this integral. So now in order to find this integral, we do have to find the antiderivatives, and then we evaluate from 0 to 1 and then from 1 to 2. So what I'm going to do is I'm going to find the antiderivative of 8x. So the way I'm going to do this is I'm going to factor out the 8 and focus on the x. Now the x is a power function, so in order to integrate I add 1 to the power. So since this is to the power 1, it now becomes x to the power 2. I divide by the new exponent, so I get 8x squared over 2. I'm going to also integrate x squared in the same way. I'm going to add 1 and get x cubed, divide by the new exponent is 3, and then evaluate from 0 to 1. Then I'm going to add in the second integral. And as I look at this next one, I'm going to again factor out the 8, and I need to integrate 1 over x. Now, 1 over x is the same as x to the negative 1, but I can't use the power rule because that doesn't work for negative 1. Instead, we have to recall that the antiderivative of 1 over x, or the indefinite integral, is natural log of absolute value of x. So we get the natural log of the absolute value of x. Then, again, we subtract off the integral of x squared, which was x cubed over 3, and then I evaluate from 1 to 2. Therefore, in order to get my total area, I have to plug 1 in and subtract off 0, plug 2 in and subtract off plugging in 1. So what I get is 8 times 1 over 2 is just 4. 1 cubed over 3 is 1/3. Minus, if I plug 0 in, I just get 0 here. So that'll give me the first area. Plus, now I plug 2 in, I get 8 natural log of 2. Minus 2 cubed is 8 over 3 is 8/3. Minus, and now I have to plug 1 in, so I'm going to get 8 times natural log of 1 minus 1 cubed is 1 over 3 is 1/3. And so now it's just a matter of simplifying. If I do that, 4 minus 1/3 is 12/3 minus 1/3 is 11/3 plus 8 times the natural log of 2. And then I have minus 8/3, and then I get minus is plus 1/3. So now if I combine that together, I have 8/3 minus, or 11/3 minus 8/3 is 1, plus 3 is 4/3. So I end up with 4/3 plus 8 times the natural log of 2. Now, if you'd like that as a decimal, you can plug that in your calculator, but I'm going to leave that as is because that is giving me my total area. And so what we have found is that the area bounded by these curves is going to be precisely 4/3 plus 8 times the natural log of 2. Alright, thank you for joining me for calculus practice. If you'd like to see more problems, you can check out the rest of this playlist available up here. Also, please sure to subscribe to the channel so you can see when we have more of these coming up. In addition to that, you can also check out the link available in the description below to see the written version of each of these problems so that you can pull that up to follow along with the video or to do on your own for extra practice. Thank you and good luck with your studying.